Welcome to ECE 382 Embedded Computer Systems 1. I'm Captain Stephen Beyer, and I'll be providing you these videos for each lesson throughout this course. These videos will be watched prior to class and will prepare you for the in-class lab activities. Content from these videos will be on pre-labs and tested through GRs, but really the goal is to have you prepared for the lab prior to showing up to class, whether that's synchronously or asynchronously. So today in this video, we're going to just kind of introduce what embedded systems are, what is a microprocessor, microcontroller, and kind of just go over that general information. So what is an embedded system? From Wikipedia, it's just a computer system that has a processor, memory, input-output devices. So that could be sensors. Think of anything along the lines of, maybe motors, or for our robot, we'll have bump sensors on it. Any input-output devices, and then it has a dedicated function within a larger system. And for example, our robot, that dedicated function will be driving through a maze. But you can think of maybe a toaster. That is an embedded system. That's a dedicated function to toast bread. And there's numerous examples. But like we said, it includes a microcontroller or computer. So that's your brains. Key is performs a dedicated or specific task. It's constrained. So what we mean by that is there's limits. Typically in software, you do maybe have a memory limit, but with an embedded system, you have a lot more things to think about, whether that's price, power, safety. So in a vehicle, there's tons of embedded systems, and those embedded systems have to be constrained by how fast they react. And so safety is a huge part of that. They have to operate in real time, typically, and then with the physical world. So that's one of the big things that differentiates an embedded system with something just software. And then typically there's small memory requirements. So like we said already, tightly constrained, but small memory requirements compared to, say, a general purpose PC. So for example, the MS432 that we'll be using for the robot, doesn't have terabytes of memory. All right, so let's talk about applications. And there's tons of applications, but these are some of the major areas. So communications, so your cell phone is one giant embedded system. Aspects of it, are very software based, but since you have your speaker, you have the camera, all of these different wireless, Wi-Fi, Bluetooth systems, and those are all working with a computer. Nowadays, phones are getting so smart, so much memory. It's almost a general purpose computer, but you can still think of it as an embedded system since it does interact with the physical world. Automotive is huge. So whether that's the safety systems, so your airbags, any aspect of it, automatic braking, all of those are connected to a computer and interact with the real world. So automotive is huge. Military, so the smart bombs, any of those devices, radios, anything that we're using in the military, a lot of those are now embedded systems. So when we think of the SDB2, the small diameter bomb 2, that has a computer on board. It's using GPS. It's interacting with the guy on the ground, the JTAC, who can dynamically retask that bomb after it's off the aircraft. So it is a very some of these weapon systems have very advanced embedded systems and computers in them. Medical. So whether that's a embedded system in the body, so something that's helping the heart continue to beat. It might be communicating over Bluetooth with a phone, and then now you have this embedded system, well, literally embedded in your body, but it has a computer in there and it's communicating and it's interacting with that physical world. Consumer electronics. So refrigerators nowadays, they can communicate with other devices in your house. You can tell if the door's been left open. As we get smarter and smarter and think of the Internet of Things, all of those Internet of Things are embedded systems. Those are computers typically interacting with the real world. So whether it's a light bulb or a switch, all of those are now getting smarter and smarter, and we have more and more embedded systems around us. And then industrial control systems. These are huge. When we talk computer security, you think about our power grid, you think about our water supply. All of those now have different components along the line controlling, motors, generators, all these different things now have computers, network access, and this really creates this world where we have to think about all these embedded systems, security of the embedded systems, and how is that interacting with our physical world. And I've said it a number of times, physical environment. So embedded systems react and interact continuously with our physical world. Inputs come in, we perform some calculation, and then our output is some kind of result. So on our robot, we have our bump sensors. We hit a bump. That's going to send a signal to the MSP432 or our computer. We're going to do some kind of logic, and we're going to say, hey, we see this bump. We need to stop the motors. And when we start talking about these constraints and real-time interacting with the physical world, that has to happen fast. We think about the airbag in the car. That has to be, nanosecond response time. So we have to think about this embedded system. How fast is it? How much power does it require? We can't have it slowing down because it's using too much energy or too much power. So we have to think about all of those different things when designing our embedded systems. And there's different ways to think of embedded systems, but let's take a look real quick at our what our robot will look like. So this is the TI, Texas Instruments Robotics System Learning Kit. So that's your robot. Hopefully you got yours by now. It includes the microcontroller. So that's the MSP432. Microcontroller is, you can think of it as a small computer. It doesn't have a lot of memory, doesn't have a lot of processing power, but it takes care of what it needs to. So it does have a processor, RAM, and then the big thing is your input-output ports that are connected to your motors, your bumpers, line sensors, distance sensors eventually. And all of those things are working together, but it's a collection of subsystems. So, the motors alone are a system. We're going to design that system separately. The bumpers, once we have the information, how do we take that signal and then what do we do with that? That's a whole system on its own. So each subsystem has its own characteristics, timing bounds, and documentation. And we'll look through all that during the in-class portion during lesson 1, and we'll look at where all that information is. But you think we design our motors, those have to operate at a certain rate, and then so that we can go certain speeds. That's going to be 100% different than maybe the bumpers, which are going to have to react much faster than potentially the motors. And there's a number of data sheets we'll look at throughout this course. For example, the bump switch will have its own data sheet, it has its own characteristics, how fast does it respond, etc. and etc. And I kind of hinted to it, but we will design this in different sub-level design. So system level development is called hierarchical development. What that means is you have your different levels, so low, medium, and high level design. So let's say, for example, our low level is our bump sensor. So that is literally just the piece of code that's saying, hey, if it's a, if I have this signal, it's a 1, and if I have this signal, it's a 0. So if the button is pressed, it's a 1, and if the button or the bump is not pressed, it's a 0. And then we have maybe our motor, and that's going to be our pulse width modulation, so our 1s and 0s that we're sending to that motor to drive that motor forward. So those are two different low-level systems, all separate, but then we talk about medium level. So we could potentially, every time we get a bump, we could stop motors on bump. So that's a medium level, system level design. And then our high level could be, say we have our line sensors over here as well. Our high level could be follow a line until bump and then stop. So that is a higher level. That is basically thinking of, when we went back up here, that dedicated function. So that overall function of the robot here will be driving and following a line through a maze until a bump. And so that's where you get your high. So our low was the bump and motors, maybe the line sensors. Medium was stopping the motors on a bump. Maybe over here, on the left side of the line sensor, if it's left of the line, drive one motor faster than the other. And now our overall high system is what is that primary task we were trying to do. All right, so let's talk a couple big ideas real quick with embedded systems. So we have to, there's a lot of things going on in hardware and software, and we have to make sure that what we want, that dedicated task, we have to know if that task is working, and we have to prove that it's working correctly. So there's four main things that operations managed by the operating system that kind of we'll be looking at throughout the course. So there's synchronous events, so protocol where two devices share the same clock, and this should be a little bit review from 281. So that would be potentially, the left and right motor, they're going to share the same clock. They're going to both be operating at the same kind of pulse width period, and they're going to be synchronous. Asynchronous are protocols where two devices do not share clocks. And we'll see that a lot in this course. For example, the distance sensors that we're going to add to the robots, those are going to operate at a different period than the motors. And then also you can think of asynchronous might be like the bump, someone hitting the bumps, the robot running into the wall. That's not going to be based on any kind of clock. That's going to be asynchronous. It's just going to happen when it happens. And then there's two types of processing, concurrency and parallelism. So concurrency is doing two things at once, but switching back and forth using interrupts. So this is not parallel processing. We're going to do one thing until someone else tells us to do something else. So for example, we are going to be driving the robot until a bump sensor is hit. Once that bump sensor is hit, we're going to stop that process of driving the robot. We're going to look at the logic of the bump sensor, and then we're going to go back to figuring out, hey, what are we supposed to be doing? Should we now drive backwards? And that's that switching concept. And we use interrupt. And we'll learn all about interrupts throughout this course, what that means. But for example, on your computer, the operating system is looking at interrupts all the time. So as soon as you hit like the W key on a Word document, that's going to interrupt the processor, and it's going to, then put up a W. So there's lots of interrupts, lots of concurrency in general purpose processing. And then parallelism is doing two or more things at the same time using multiple cores. And that is what we see a lot more nowadays with your quad-core processors, your GPUs. And so what we will primarily see in the MSP 432 is concurrency. We'll be switching back and forth between different processes. All right, so let's talk about a little bit more about constraints. So we briefly talked about it. There's a lot of them. Size of the system, does it have to be in a phone? Does it go in a car? Is it going to be on an aircraft? Changes the size and weight. You can only put so much weight on an airplane before you start getting into your bottom line of personnel or materials. How much power does it require? Can we do it on 9 volts, 12 volts, 120? Cost, of course. A lot of these IoT Internet of Things devices, they want to be cheap. Environment, are they going to be outside? Are they going to be inside? Is there going to be heat, vibration, water, corrosion? And then safety, critical operation. That's a key thing to keep in mind when designing an embedded system. Is this a safety critical operation? So that means it must function correctly. You can't have your airbags have a malfunction during a crash. And must not function incorrectly. All right, and the last main topic I want to talk about is timing. So this, again, you can think about this with your safety critical operations, but hard real time means we guarantee that process will complete a critical task within a certain time. And the consequences, so let's talk consequences of a hard real-time event not meeting that are catastrophic. So firm real-time, but let's talk about also value of missing deadlines. So for hard real-time, if we miss a deadline, it's going to have a negative value. And that means, we just don't, it's going to be bad. All right, firm real-time, we expect all critical tasks to complete on time, and then it ignores values after deadline. So we expect to complete on time, and we ignore late data. Consequences for firm real-time are Nothing bad's going to happen because we're just going to ignore it. But also nothing good comes from it because we're ignoring that data. The value of missing it is just 0 value. So like I said, we're just ignoring that data. So for hard real time, we can think of those as emergency systems. And then for firm real time, think of this as like streaming audio, where we can lose packets, we can lose data, and we'll still be able to still have a good song. If we start losing quality of the music, if we lose too much, obviously the song's going to start sounding bad, but we can lose some data and still be fine. And then soft real time is our best effort. We're going to do our best. Doesn't really matter, but over time it's going to get worse and worse and worse. And then by the time we lose everything, obviously we have nothing good. And we can think of this as operator commands. So if I am driving a robot with a keyboard, and I tell it to go left, and it takes half a second. In my mind, that's as we are looking at it, it's not going to matter. But over time, it takes 2 seconds, 3 seconds, then it's going to get worse and worse and worse. The other idea is displaying to an LCD. Our eyes can only see so fast, and it won't, over time, yeah, it'll get really bad, but right away, no big deal. So still some good if we finish after the deadline. So that's no consequences really, unless you're really, really late. And over time, the value of missing it is some value, but diminishes over time. So those are our 3 timing constraints. Hard real time, we want it done right away. Firm real time, we want it done right away. We're just going to ignore anything that comes later because it's going to mess up our data, but it's not going to hurt anyone or anything. And soft real time, we can accept data that's late, and it's going to still provide us the goal that we want. All right, and the last little thing is, why do we use embedded systems? And I have here a table with 4 different, kind of computer systems. So an Arduino, which is your, really basic kind of micro controller. Raspberry Pi 3B Plus, which is kind of getting bigger to your microcomputer. And then our MSP430, which was the microprocessor we used prior to 2 years ago, we were using the MSP430. And then now what we're using, which is the MSP432. And we look from left to right, the cost, if we go down to the bottom. One of the main reasons we use embedded systems is because of this cost difference right here. So we go from $35 to a couple dollars, and then we go really low to Arduino to $1. And you can think, if we have a lot of these systems, we want to keep it cheap. Memory, so while the Raspberry Pi 3B Plus has 1 GB of RAM, Raspberry Pi 4 has 8 gigs of RAM. Our Launchpad only has 256 kilobytes. And that allows us to have less power, but it also slows down the processing. And then we can look at how much input output do we have. So our MSP432, 84 general purpose input output pins. That gives us a lot of capability to communicate with a lot of devices. Raspberry Pi, not so much. And the biggest issue with the Raspberry Pi is that's a whole computer with an operating system. So when we talk about those real-time systems, we're relying on the operating system to decide, is this important enough to stop doing something else? And how much time does it take to context switch? Whereas the MSP432, whatever is programmed, it doesn't have an operating system to tell it otherwise. So it's really, really powerful, MSP432 embedded system, It allows us to meet the constraints we need. And as we go down the line, we might need to go something more powerful than the MSP432. So in the capstones, they're using Raspberry Pi 3B pluses with the MSP432. The MSP432 does all the driving and bump sense control to stop the, if there's a collision. And the Raspberry Pi 3B Plus is doing, vision, navigation, etc. And so now we combine these systems, and we're getting this, larger, more powerful system. So that's why an embedded system is really helpful. This, controlling the motors, driving, all of that, we don't want to pay $40 to do that. We just want to do that a couple of dollars. We want it to be fast. We want it to be low power. And then the Raspberry Pi 3B Plus can come in and help us with all those other things. So that's it for today. Assignments. We'll go through the pre-lab, and then next time in class will be the Module 1 lab. So accomplish this pre-lab. It should only take you a few minutes, hopefully just about 20 minutes, to download the software you need for the course, and then just get the starter programming set up, and then you'll be good to go for the in-portion class lab.